Greetings, everybody. Learning as a hobby here. In this video, I want to go over my summary for section 1.1 in Kenneth Rosen's Elementary Number Theory and its applications. I have an older edition. This is the fifth edition. I think it's in later editions now. I don't know what the most recent one is, but this is the one that I have. So this is the one that I'm going to go through. And like I said, this is section 1.1, which is a relatively short section. Um, so. Uh, there's a bunch of sections in chapter one. It's I'll be posting the videos for those, in the upcoming weeks and so on, along with my videos on Ivan Niven's book. Uh, and I got the exercise sets coming up for both Niven and for section 1.1 in Niven and in Rosen shortly. But anyway, sorry, I'm rambling a little bit because I just woke up. I haven't had my coffee yet, so I have it here next to me. My wife and I are going to go to the botanical gardens and spend the day there because it's a beautiful Sunday here in New York City. Which, if you haven't been to the Bronx Botanical Gardens and you have a chance to visit New York, definitely go make that one of your stops. It's a wonderful green space. Anyway, let me bring up my notes and we'll go through this. Okay, so section 1.1. We start with some definitions and, well, an axiom, I guess. Section 1.1 is on, sorry, yeah, the entire section 1.1 is on numbers and sequences. We'll start with the definition of the integers, or an intuitive definition, I guess. The integers are the numbers in the set, dot, 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 -3, -2, -1, 0, 1, 2, 3, et cetera, et cetera. And we start with an important property of the integers, which is called the well ordering property. I already talked about this in Niven, but again, most number theory books start with this because this property is what you use a lot of the times to prove things about integers. So anyway, that in mathematical induction, which is actually equivalent to the well ordering property. But anyway, here's what it says. Every non-empty set of positive integers has a least element. Right. The well ordering property may seem obvious, but it is the basic principle that allows us to prove many results about sets of integers. And the well ordering property can be taken as one of the axioms defining the set of positive integers, or it may be derived from a set of axioms in which it is not included. Rosen suggests, uh, taking a look at Appendix A, which actually, let me take a look here. I assume that Appendix A maybe is on the construction of the integers, but let me take a look and see. Let's see. Appendix A are it's the so Appendix A is the axioms for the set of integers. There's appendices B, C, D, and E as well, which is Appendix B is on binomial coefficients. Appendix C is on using Maple and Mathematica for number theory. Appendix D is number theory web links, and t Appendix E is on, I guess, tables for number theory. I don't know. I haven't looked at it, but I wonder if the web links are still valid because, like I said, this book, the fifth edition, is kind of old, so I don't know how many of those links will still be active or not. But I guess we'll see as we go through the book. Anyway, we see that the set of positive integers is well ordered, or sorry, we say that the the set of positive integers is well ordered. Again, you gotta excuse me. I just woke up and I need some coffee. All right, here's a definition. The real number R is rational if there are integers P and Q with Q not zero, such that R is P over Q. And if R is not rational, it is said to be irrational. All right. And then we have our first theorem, which is that square root of 2 is irrational. And we've seen proofs of this already, but Rosen gives a sort of an alternative proof using well ordering. That is interesting to see because usually the one that you see is the one where you derive a contradiction that if square root 2 is rational, then it's in the representation that you have P over Q is in reduced form, and then also that it's not in reduced form, and that gives you the contradiction. Here we get a different contradiction using well ordering. So it's an interesting proof to see just for, an alternative proof of this. All right, so assume square root 2 is rational. Then there are integers a, b not 0, such that square root 2 is a over b. Consider the set S, which is the set of all k times square root 2, where k and k times square root 2 are natural numbers. Then b square root 2 equals a is in the set S, so S is not empty. Therefore, by well ordering, S has a least element, which we'll call t times square root 2. We'll call that little s. Then consider the element s, or the natural number s root 2 minus s, then 0 less than s root 2 minus s, which is equal to s times root 2 minus 1, since square root 2 is bigger than 1. Also, s square root 2 minus s is equal to s times square root 2 minus t square root 2, which is equal to s minus t times square root 2. And also s square root 2 is 2t, which is a natural number, and 2 times square root t is also a natural number, which implies that s minus t times square root 2 is a natural number, which means that s square root 2 minus s is an element of the set S. And lastly, s equals square root 2t is greater than 2 minus square root 2t, which is equal to s square root 2 minus s, since 2 greater than square root 2 and 1 minus square root 2 is bigger than 1 and less than, bigger than 0 and less than 1, which implies that 0 less than 2 minus root 2 less than square root 2. However, s square root 2 minus s less than s contradicts the fact that s was the least element of the set S. Therefore, square root 2 is not rational. That's we get our contradiction there. Okay, so an interesting sort of different proof of this that you don't often see in, for example, analysis, because here we're using the properties of integers. Okay, another definition. A number alpha is algebraic if it is a root of a polynomial with integer coefficients. That is, alpha is algebraic if there exists integers a0, a1, dot, 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 up to an, such that an x to the n plus an minus 1 x to the n minus 1 plus dot, 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 plus a0 equals 0. The number alpha is called transcendental if it is not algebraic. And then just a note, all rational numbers are algebraic, since if a over b is rational, then a over b is the solution to the polynomial equation bx minus a equals 0. Right? Another definition, the greatest integer in a real number x, denoted by, here we use Rosen uses square brackets around the number x to denote the greatest integer of x, is the largest integer less than or equal to x. That is, the greatest integer in x is the integer satisfying um, the greatest integer x less than or equal to x less than or equal to the greatest integer in x plus 1. All right, and just some other notation here. If you're a computer science person, you've probably heard this stated in a different, or called a different thing. The greatest integer function is also known as the floor function. This is sometimes denoted like this. So instead of like the square brackets, you have just brackets with the little tails on the bottom. And then there's also the ceiling function, which we denote with the same symbol, but with the tails on the top, which is defined to be the smallest integer greater than or equal to x. Right? And we get an example here, which is a proposition. Show that if n is an integer, then the greatest integer x plus n equals greatest integer x plus n whenever x is a real number. So here's my proof. By definition, the greatest integer in x less than or equal to x less than greatest integer x plus 1. Then for any n in z, excuse me, greatest integer x plus n less than equal x plus n less than greatest integer x plus n plus 1. Then by definition, the greatest integer x plus n is the greatest integer less than or equal to sorry, that should be greatest integer equal to x plus n. Sorry, let me just fix this real quick. All right, which implies the statement. Okay, another definition. The fractional part of a real number x, denoted by set brackets around x. This doesn't denote a set here. By the context, it should be clear. It's not a singleton set. It's the fractional part of the real number x. So if you see that here in Rosen's book, by the context, it should be clear what we mean, is the difference between x and the largest integer less than or equal to x. That is, the fractional part of x is equal to x minus the greatest integer in x. All right, and just a note, the greatest integer of x less than or equal to x less than greatest integer x plus 1 implies that 0 less than or equal to x minus the greatest integer in x less than 1 for every x in R. The greatest integer in x is also called the integral part of x because x equals greatest integer x um, plus the fractional part of x. Right. So in other words, the fractional part of x is always between 0 and 1, right? Less than, greater than or equal to 0, strictly less than 1. Okay, then we get to Diophantine approximation, which is an interesting section. Uh, First, he explains what Diophantine approximation is. It's a branch of number theory that studies approximation of real numbers by rational numbers, and we're going to prove an important theorem in Diophantine approximation. But before that, we need to use theorem 1.2 as a lemma, which is the pigeonhole principle. Again, you might have heard of this before, but let's state it out and then prove it. So if k plus 1 more objects are placed into k boxes, then at least one box contains two or more of the objects. And here's my proof. Let S be a set where the cardinality of S is k plus 1 for some k in the natural numbers union with 0. Let T be the set of singleton subsets of S and assume that the cardinality of T is K. Then cardinality T equals the sum of the cardinality of the singleton sets from the set S, which by assumption, the cardinality of T is assumed to be K, but the number of elements in S is K plus 1. So K equals K plus 1, which implies that 0 equals 1, which is a contradiction. So that proves the pigeonhole principle. Right. And then he has a historical note here. One nice thing I should make an aside here. One nice thing about Rosen's book is there's a lot of historical biographies of famous mathematicians that have done work in number theory, which is pretty cool about this book. But he says the pigeonhole principle was first introduced by Dirichlet. If you don't know, Dirichlet he was a very important mathematician that did a lot of work in analysis and also number theory. Okay, and then he just refreshes our memory here about some definitions. The absolute value of a real number x is defined to be x if x is greater than or equal to 0, or negative x if x is less than 0. And the absolute value of x minus y gives the distance between x and y. Right, and then we get to Dirichlet's approximation theorem, which is theorem 1.3 in the book, which says this: if alpha is a real number and n is a positive integer, then there exist integers a and b with a greater than or equal to 1, less than or equal to n, such that the absolute value a alpha minus b less than 1 over n. And let me just say here a quick note about uh, this proof is very I find this proof to be very beautiful. Um, it's a simple sort of statement, and it's probably obvious from looking at it, like if you've taken a course in analysis and so on. Not obvious, I shouldn't say obvious, uh, but in analysis we know that the real numbers satisfy the least upper bound property, and it's Archimedean. So with those things, you can prove similar types of things. But anyway, this is a number theoretic argument, and it's involves a really clever sort of observation, and the proof is just great for I don't know if someone would come up with this, a student that's just seeing number theory for the first time would come up with this proof themselves, but it is a great example of a nice simple proof in number theory that is just shows the sort of beauty of the subject. So anyway, let's go through it. Okay, let alpha be a fixed real number. Consider the n plus 1 numbers, 0, then the fractional part of alpha, the fractional part of 2 alpha, and so on, up to the fractional part of n alpha. Then 0 less than or equal to the fractional part of j alpha less than 1 for each j 0, 1, 2 through n. Each fractional part of k alpha is in an interval j where the interval goes from j over n inclusive to j plus 1 over n not inclusive for j 0, 1 through n minus 1, and each of these intervals is disjoint from the others. So by the pigeonhole principle, or in other words, theorem 1.2, at least two of those fractional parts lie in the same interval. Here I'm calling it j over n to j plus 1 over n for some j. Then, for example, say k alpha, the fractional part of k alpha and the fractional part of t alpha satisfy this condition. Then the absolute value of fractional part k alpha minus fractional part t alpha less than 1 over n, right? Because the width of each of those disjoint intervals is 1 over n. And choose a equal k minus t and b equal to the greatest integer in k alpha minus the greatest integer in t alpha. Then the absolute value of a alpha minus b is equal to the absolute value of k minus t times alpha, excuse me, minus the greatest integer in k alpha plus the greatest integer in t alpha, which, rearranging some things, gives you absolute value kd minus uh, greatest integer k alpha minus, in parentheses, t alpha minus greatest integer t in t alpha, which by definition is equal to the absolute value of greatest integer k alpha minus greatest integer t alpha, which we know is less than 1 over n. So that's the proof of Dirichlet's theorem, which, like I said, I really like this proof a lot. I think it's super sort of pretty, I guess, if you could say such a thing. Anyway, so that's the proof of Dirichlet's theorem. And the nice thing about Dirichlet's theorem is it gives us a nice way of approximating irrational number or any real number, even rational numbers by rationals. So suppose that alpha equals square root 2 and n is 6. Here's example 1.6. Then if we take 1 times square root 2, 2 times square root 2, all the way up to 6 times square root 2, we take the one of those numbers that has the smallest fractional part, which in this case is 5 square root 2. And that means that um, we can choose A to be 5 and we can choose B to be 7. And that gives us 5. So then that means absolute value 5 square root 2 minus 7 is approximately 0.071, which is obviously less than or equal to 1 over 6. In other words, for alpha equals square root 2 and n equals 6, a equals 5, b equals 7. I just said that. But so that means that square root 2, you can use the approximation 7 over 5 and for square root 2, and you'll be within 1 over 6 of the actual value of square root 2. So kind of a neat theorem. Okay, just another note. The above proof shows Dirichlet's original 1834 proof, proving a stronger version of theorem 1.3 with 1 over n plus 1 instead of 1 over n. 1 over n is not difficult, and Rosen says see exercise 32, so I suppose we'll be doing that ourselves and when we get to the exercise set. In exercise 34, we show how to use Dirichlet's approximation theorem to show that given an irrational number alpha, there are infinitely many different rational numbers p over q, such that absolute value alpha minus p over q less than 1 over q squared, which is an important result in the theory of Diophantine approximation. So we have some exercises to look forward to later on. Okay, then the next section here in section 1.1 is on sequences, and we start with the definition. Sequence, which we denote like this, hopefully you're familiar with that. That notation is a list of numbers A1, A2, A3, dot, dot, dot. The terms of a sequence can be put into a one-to-one correspondence with the set of positive integers using a mapping f of I equals a sub I. And Rosen reminds us that a one-to-one correspondence, also called a bijection, is a function that is both one-to-one and onto. All right, and then we get some examples and some definitions. A geometric progression is a sequence of the form a times a comma ar comma ar squared, all the way up to r to the k, and it goes on forever, right? Where a is the initial term and r is the common ratio, are real numbers. All right. Then we get to an example. I'll skip the examples. He just gives us examples of some sequences. The first example is arithmetic, so we define what an arithmetic progression is right after it. An arithmetic progression is a sequence of the form a plus d, a plus 2d, a plus 3d, et cetera, et cetera. So you have the initial term is a, and the common difference is the number d. So it's sort of like a discrete linear function, if you want to think of it that way. Also, geometric progressions you can think of as discrete exponential functions. Okay. Let's see some more examples of sequences. He gives us the Fibonacci sequence here. Like I said, I'll skip over this because I don't know if you want to, if you want to stop and pause your screen and look at it, you can. But it's pretty straightforward. Um, we get to this definition here. A set is countable if it is finite or it is infinite, and there exists a one-to-one correspondence between the set of positive integers and the set. A set that is not countable is called uncountable, right? And we have an example here, which is an important example for when we get to the proof of the next one. So the integers are a countable set because we can list them. For example, if we let a sub j equals 0 if j is 1, n if j is 2n, and negative n if j is 2n plus 1, then we get the sequence here, which notice gives you every integer within some finite number of entries. Okay, so that's an important sequence because we're actually going to use that in theorem one in our proof for theorem 1.4. So the set of rational numbers is countable, right? Which maybe sounds counterintuitive, but in fact they are, and we'll prove that here. So here's the proof. Create a rectangular array below using the rational numbers. List the rationals in the order suggested by the red arrows. So here I have the picture drawn. So notice for each row you have the denominators increasing by 1. So you start with the denominator of, sorry, this should be 1 here. Okay, you start with a denominator of 1, then the next row has all the denominators, all the fractions that have the denominator 2. Next row has all the fractions that have denominator 3, and so on and so on. And then the numerators are the sequence, progress in the sequence according to the sequence that we defined here in exercise 112, right? And then you count the rationals along the arrows. So follow the arrows. So first, here I have it written down here. The first entry would be in the sequence would be 0 over 1. Then the next entry would be 1 over 1, then 0 over 2, then negative 1 over 1, then 1 over 2, then 0 over 3, and so on. You keep going like that in this sort of diagonal way. And you throw out the repeats. So there's no need to write the repeats. So when you come across a rational number that you've already listed, just throw it out and go to the next one. All right, so this gives the rationals as an ordered list, which means that they're countable. For example, for any rational P over Q appears in row Q in the column 2P if P is positive and column 2P plus 1 if P is negative. So P over Q will be listed in less than Q times 2P plus 1 entries. So that's a very loose upper bound, but all that we care about is that it's each integer, sorry, not each integer, each rational is listed within some finite amount of time, or a finite number of entries, and that's the case here. So we get a sequence of rationals here, which means that they are countable. Okay, and that's the last thing in section 1.1. Let me just stop my screen share. All right, like I said, I'm in the middle of the exercise sets for section 1.1 in this book and also in Niven's book. So those try to get those out at some point soon. And I haven't started on the exercise set for chapter 11 in yet, but I do want to do that. I may sacrifice my back and bring a Spivak with me to work this week and try to get started on that exercise set in between my classes. So, all right. Anyway, I'll leave this video here. Let me know what you guys think down below, and I'll see you in the next video.